All right. So, as a reminder, there is homework due Wednesday, right, in class. So, make sure if you haven't started it, you get going that homework, get it finished by Wednesday. That's it for kind of just general announcement stuff. Are there any comments, questions, issues with my most recent quiz?
I have a question about number 2 and 4.
Okay.
I have a question about number 2.
All right, so a bunch of people about the quizzes online. All right. Let's find out if some typos or what's happening. Equilibrium. All right. Screen. Okay. So start number 1. So there's question number 1, right? So, right in this problem, okay, we have the dissolution of magnesium chloride, right, MgCl2. Okay. We know that in the solution that has some solid magnesium chloride in equilibrium with magnesium chloride ions in solution, that the activity, which is the effective concentration of magnesium 2+, is 0.13 molar. And the question is what is the equilibrium constant that KSP, right? So recall, right, SP, solubility product, that's just talking about the type of equilibrium, right? This is a solubility equilibrium, so it's solid MgCl in equilibrium with Mg2+ plus 2Cl minus ions, right, is the equilibrium. And so KSP, the expression for that, right, right, the expression for KSP for that reaction with concentration of Mg2 plus times concentration of Cl minus squared, right? And then again, you're told the activity was 0.13 molar. You're told, right, that the effective concentration of Mg2 plus, right, the activity, right, that's that like effective concentration, right, is 0.13 molar. Okay. Well, how this Mg2 plus ion got into solution, right, is from the dissolution reaction, right, the reaction MgCl2 going to Mg2 plus 2Cl minus, right? And so if in this process, right, I get an effective concentration of 0.13 molar here, right? That means the effective concentration of Cl minus has to be 0.26 molar, right? Just twice that because the stoichiometric coefficient of 2 here, right? So then I just plug that in to the KSP expression above and get numerical value. That hopefully is the value and the answers. So anyone have any issues with problem 1 in terms of they felt like they entered things incorrectly and got the wrong numbers? So otherwise I can check numerical. All right. So no questions about that. No one online. Okay. So yeah, so that's what number 1's getting at. All right. So I will say, right, with this equilibrium stuff, okay, if you don't recall some of your stuff in chemical equilibrium from general chemistry or wherever else you maybe have done it, you know, potentially just kind of review that briefly, you know, because we're not going to spend time in class reviewing what we hopefully learned in Gen Chem and stuff, right? I know it's been a while, and so it might not be very fresh in your memory, but yeah, so like if that KSP was kind of throwing you off, right? Suggest just kind of reading over that briefly. So would it be 0.13 times 0.6 squared? Yes. Daniel, or Danielle, sorry. That would be what it is. Again, hopefully that's what I have for the answers.
It is.
Okay. Fantastic. All right. So question number 2. What is the ionic strength of a solution that contains 0.045 molar AgCl3 and 0.03 molar BaCO3?
How do you have AgCl?
That's quite the first question.
Because AgCl works for aluminum chloride like that, but Ag, because I treated it like it was +3, but then I was looking that up and I can't work. Yeah.
Then maybe I should have done aluminum. I don't know. I just put some stuff together. So this is PChem, right? This is not inorganic chemistry. This is not organic, right? This is PChem. So you know my compounds and such. I thought silver could have a +2 charge. Guess not. No.
And what I read,
+1 and only +1.
All right.
It says sometimes +2 what I read.
So maybe it was aluminum is what I was thinking of in my head. Can't aluminum have +3?
Aluminum chloride is that.
Yeah. Okay. So I was thinking of aluminum and I put silver. Yeah. So yeah, I you know, so I typically, you know, an actual compound will be on exams and things like that. But you know, when I make these questions, I kind of come up with them quick. So again, hopefully, I know that's kind of confusing, but hopefully, right, just our general understanding of things that it should be Ag3+ Cl minus, right? Yeah.
Did you just work that out though? Because I treated it like 3+ and I still got the wrong answer.
Okay.
So my first question is, the ionic strength equation uses molality, not molarity, right?
That you gave us back. I don't know. Uses molarity too.
So I converted it from molarity.
Yeah, I mean, so the thing is right, to convert from molarity to molality, you need to use effectively the dense, right, assuming your concentrations are small enough, right, that the number of moles of, right, because molality is kilogram solvent, molarity is volume solution, so assuming, right, that the volume of the solution is effectively the volume of the solvent, right, then it's just basically using the density to convert, right? But then that density, but then that conversion, when you're dividing by a 1 molal versus 1 molar solution, you need to put that conversion in to that like B naught. And so, yeah, so I'll try to make sure I use molality since that's typically how it's presented in class. I forgot about that when I was doing this problem. But yeah, because of the fact that the effective ionic strength equation is like the molality divided by 1 molal, you'd have to convert 1 molal to 1 molar, and then the molality in your concentration to molarity or whatever, or vice versa, right? And so yeah, so the fact that it's in molarity doesn't actually affect the ionic strength calculation.
Do you have to know the density to be able to convert those though?
Yeah.
Yeah, because you have volume, you have to go volume to mass.
That's what I
Yeah.
thought. It was
So yeah. Yeah, so just remember, right, the ionic strength is a unitless quantity, so it's effectively dividing by the 1 molar, 1 molal. That's essentially what you have, right? But again, right. Let me see here. Let me write down these numbers. So 0.045, 0.03 EgCl3, and oh, you know what? I wonder. We'll find out. All right. So that's what we have. Again, right, the idea, again, if I had some solution that was like 0.05 molal, it would also be divided by 1 molal, right? And if I need to convert that to molarity or something like that, I would, you know, molality is what, per kilograms. I want per volume. So I want kilograms per volume, which is density, right? So I'd multiply by the density of like water, and I'd have to multiply the top part by the density of water, right? And that would give me things in molarity, but those will cancel, right? And so yeah, so back because in the ionic strength equation, right? If you recall, right? That's so weird. Coughing or something with the mask on. I'm like, I don't know what to do. I feel like I want to take off the mask and then cover my face out of habits, right? But anyways, sorry, I was online. Didn't see me do that. Let's see here. So 1/2, right? Then it's times, right? The charge squared, right? Essentially, the sum of the charge squared times the molality, or in this case, molarity, right? Divided by B naught, right? If you will, right? Where B naught is 1 molal. Okay, that's essentially the equation. Okay. And so for our problem here, right, it's 1/2. And then let's start with AgCl3, right? So I like to do it like this. So I'd have 0.045 times, then for Ag, it's a charge of 3 plus, but its concentration is just the 0.045. So it's going to be 9 times 1 plus, then for the Cl3, it has a charge of 1, but then its concentration is 3 times 0.045. So times by 3. Okay. Right. And then, yeah, so I'm multiplying 0.045 by all of this. And then the other one is 0.03, and then times, both these have a charge of +2, okay? But then they're, you know, but they both have a concentration of 0.03, so it's 4 plus 4, okay? And so this is I equals 1/2 times, let's see here, so 0.04, let's see, 9 plus 3 is 12. So actually, let's get rid of that 1/2. So 6 times 0.045 plus 0.03 times 4. Okay, so I got rid of I multiplied the 1/2 through, right? This is 8 divided by 2, which gives us 4. And then this is going to be 12 divided by 2, which gives us 6. Okay. And then hopefully that comes out to the number I have online. Does not? Oh my goodness.
Yeah, I think that what you did is that you put the charges for
So here's
Ca and CO3 as +1.
Could you have done silver chloride, but the chloride was just like.
I think I forgot the charge. I think kind of what was being said. I think because as I was about to do this and say this to you, it dawned in my head that, I don't know, like I all of a sudden thought back when I was doing the solutions and thinking, you know what, I focused on the concentrations being 1, but I don't remember if I thought about the charges being +2 and +2, or +2 and -2. And so, yeah, I think 0.12 plus 0.27. So yeah, so I here is equal to 0.39, which I guess I have 0.3, right? So, all right, so woohoo, I get to manually regrade all of that. Fantastic. Yeah, so sorry about that. That was on me. So the questions about this. Yeah, again, sorry about those who actually thought about, chemistry while doing this problem. Like AG should just have a charge of +1, right? And not kind of how I wrote the formula. Right. Yeah. That's might not have been the first time I wrote something like that. Some weird molecule or something happening that doesn't actually happen. So. All right. And then there was a question about number 4. Is that right?
Yeah.
All right. So for this one, right, you just use that relationship between delta G and K, right? Back to delta G, right? So what we're trying to calculate is just minus RT ln of K, right?
That's what I did. It was wrong.
Did you convert from joule to joule?
Yeah.
Yeah. See here, share.
I got it right. I got it right. It's correct.
And K is equal to 0.0.
The answer should have been when you put it in. Yeah, I know.
I had it written on my paper negative, but I
Oh,
put it in as positive. But the answer is supposed to be negative?
Yeah.
Yeah.
Should be negative.
Um,
Yeah, it's a negative RT. You don't need to
Wait,
negative
why?
in the RT.
How would that work out?
K is ln of K should be negative. So if I have a negative answer, then actually I
The
can get
answer
that
should
wrong.
be positive, right? Because
Yeah.
the ln of K
Yeah,
is-
because K is less than 0 or less than 1. Sorry, not less than 0. K is less than 1, so delta G should be positive. So we'll see. Right. So then delta G just equals minus 8.314 times. I assume the temperature is 298.
Yeah.
Yeah. I'm going to divide all of this by 1,000. And because of the fact that this is in joules, 8.314 is joules, and the answer is asked for in kilojoules, right? And then the natural log of 0.00072. Okay. I'll just do that right now. And natural log times 8.314. So it should be yeah, so I dropped the negative too. Damn. Yeah, I should have caught that too because I'm always telling things in Gen Chem. But, oh well. So yeah, all right. So I got to regrade number 4 and number 2. I can do that after class. But yeah, so it should be a positive 17.9 roughly. Yeah, when you plug things in, right? So, it should be a sanity check that delta G should be positive, right? Because, right, a positive delta G tells you that your reaction is not going to spontaneously form products, which means it's going to favor reactants, right? And your equilibrium constant K, when it's less than 1, means that reactants are being favored compared to products. And so, right, so those should go hand in hand. That a K less than 1 means delta G is greater than 0. K greater than 1 means delta G is less than 0, right? Because both those things are indicating you're favoring products when those are occurring. Okay? So. And then obviously in the formula, there's that built-in minus sign that makes it all work out. Granted, that minus sign comes through, some of the other math and stuff. We don't arbitrarily put it there, but yeah. All right. So, any other questions about this quiz? Oh, sorry.
For activity, how do you get the
units of molarity. I thought it was like we had pressure divided by pressure, or like mole fraction times gamma. So I just didn't know how you got the units of molarity on
Question one. So activity, right? So we talked about activity in terms of molality, right? So we introduced activity and the idea of effective mole fraction, as well as like an effective molality when we talked about for a solute, right? For a solute, you can not only talk, that we not only use activity, you're talking about mole fraction, but also molality of that solute. But activity is just whatever the like effective concentration in whatever units essentially that you're using, right? That's what the activity is defined as, is essentially your effective concentration. Now, we introduced it originally for the solvent in terms of mole fraction, because we related that in with Raoult's law and such. And so that's why the effective concentration had to do with the effective mole fraction, which then related with the vapor pressure of the solvent and so on and so forth, right? But we then also talked about for the solute that you could talk about the activity in terms of the effective mole fraction, or you could talk about it in terms of effective molality, right, of the solution and such. So activity, and then activity for gases. I mean, technically, you should use the term fugacity, right? Is the activity for a gas or its pressure, right? But yeah, fugacity activity is just like the effective pressure, effective concentration, in potentially whatever units it's defined in. So, right. But yeah, and so that can impact potentially the value of the mean activity coefficient if you have different potential units or something like that. But yeah, just whatever problem kind of the units you're given for concentrations or pressures or things like that is the units to just use for activities and such. Yeah. But I should have put molality for that problem, because just like in the other problem, use molality just because that's more often what's used. I mean, what we've been using in the lecture and what's often used in the book. And just when I was writing this, I was just probably coming from doing some Gen Chem stuff, and there we mainly use molarity instead of molality and things of that nature. But right. But there's a difference between these things, right? It's just by, density of your solvent and such. But yeah, right. These problems, right? All these kind of online quiz questions are not designed to be too tricky. Hopefully you're kind of straightforward in what they're asking and what to do. Is my idea. But I know these things of giving units of molarity instead of molality and things like that can potentially trip you up, or Ag 3+ instead of Ag+. So yeah, just try not to overthink it, because obviously I didn't overthink it when I wrote these problems. But yeah. All right. So other questions about the quiz? Oh, I need to actually share that screen for people online. Okay. Okay. So let's get going then, talking about the Chatelier's principle, basically, right? So hopefully this is a refresher for everybody. Again, whether or not you've thought about Le Chatelier's principle and such since Gen Chem, I do not know, right? But the idea is, right, is that Le Chatelier's principle is related with adding some type of stress to equilibrium system, right? Some chemical reaction that's at equilibrium, adding some type of stress. We have. Right. The general principle, the idea, right, is that some chemical system that's initially at equilibrium, when subjected to stress, will react in a way to partially counteract that stress, right? And essentially what it's doing to do that, right, is it's just trying to reestablish equilibrium, right? The stress is something that takes you away from equilibrium, and it's just going to try to go back to equilibrium by undoing what you just did to some degree. Okay? Right? So types of stress and things like that are by changing concentrations of reactants and products, right? By either adding in solvent or potentially adding or removing some amount of reactants or solvents, reactants or products, right? Other potential types of stress is removing or adding solids, adding in some type of catalyst, okay? Changing the pressure by changing volume or other such things, right? Adding moving reactants or adding a non-reactant gas, or say by changing temperature. Is there going to be a question back there? Or no? I felt like you were, okay, sorry. Right, so these are different types of things that can affect the equilibrium, okay? Right, so out of these things, right, let's just kind of go over, right? If I, right, add or remove reactants or products by effectively increasing or decreasing their concentration, okay? Right, how is that going to impact the equilibrium, right? So again, assuming you're dealing with an aqueous species, for example, right? For my reactants and products, is that going to affect the equilibrium or not? I guess is the question I'm asking, not necessarily how I should say. Yeah. Yes, right? If you add or remove reactants or products, right, that are aqueous species, right, or potentially gases, right? You can talk about concentrations of gases, right? That will affect the equilibrium, okay? Right, and that will be a stress that impacts the equilibrium, and that will cause your reaction to do something to form more products or form more reactants to counter what you've just done. Okay. What about if I were to add or remove a solid or a liquid from the solution or the solvent, or I guess 2 or 3? Are either of those going to affect the chemical equilibrium? Yeah, so adding or removing a solid or a liquid, right, doesn't affect the equilibrium, okay? Because, right, you can think about your equilibrium constants, right? You're not changing things that are involved in the equilibrium constant itself, right? Again, adding, right, how each of these things potentially takes you away from equilibrium is it modifies the chemical potential of your reactants or products, right? Well, changing the pressure or concentrations of reactants or products, right, can change their chemical potential, right? We've seen those formulas, right? But then solids and liquids, okay, they by increasing their amount, right, does not change their overall chemical potential, right? The chemical potential is an intensive quantity, okay? So for solids and liquids, right, you're not changing, say, its density, right? Its chemical potential, say, is related with its density. You're not changing the density of a solid or a liquid, so it's not going to affect the equilibrium, right? For solvent, for, say, diluting the system, it really actually depends on the chemical reaction, right? Because if you think about your chemical equilibrium being a ratio of products to reactants, right, you might have, right, if you decrease the concentration of everything by a factor of 10, right, by adding in solvent, okay, depending on how your equilibrium is set up, you actually might affect what the equilibrium is, right, because you're affecting concentration of both your reactants and products. Let me just write out something, right? If I had, let's do a simple weak acid association equilibrium, right, which is essentially you have like A minus times H plus over HA, right? Remember your weak acid dissociation reactions, okay? To equilibrium constant, right? If I change the concentration of each one of these things by a factor of 10, right? Right, I decrease this by a factor of 10, this by a factor of 10, right? And this by a factor of 10, right? I will have effectively, right, changed the concentration by a factor of 10, or the Q, right? My like reaction quotient will be decreased by a factor of 10, right? It will be the original equilibrium values it was at divided by 10, right? Which is where I will be at, right? Which tells me then my reaction is no longer at equilibrium, okay? Because the effective concentrations don't give me the equilibrium expression, right? Equilibrium constant. So I'm not at equilibrium, so this thing will go away from equilibrium. So adding a solvent can change the equilibrium just depending kind of on this thing, right? It's so gases, right? Let's say I decrease the volume of a container, right, to increase the pressure in my system. Is that going to affect a chemical equilibrium reaction that has gases involved? Yes, right. Right, and how does it affect it, right? Let's say where does the equilibrium want to go if I have some chemical reaction with gases involved? What side of the reaction? Yeah, the side with less gases, right? So it's the same type of thing here, right? If you're diluting something, okay, right, it's going to depend on how many aqueous species you have in products versus reactants as to how it will, right, be impacted, right? If I have equal number of aqueous species in the reactants and product side, then nothing changes, right? The same thing with gases, right? If I have like A gas going to 2B gas, right? If I increase the pressure, right, by decreasing the volume, okay, that's going to affect the pressures of both these gases. It's going to affect the chemical potential of both these gases, right? And because I have twice as many gas over here, the chemical potential is going to be changed twice as much. And this is going to, in order to re-equilibrate the chemical potentials, I'm going to form more of A, right? So this is for like an increase in P total by decrease in volume, okay? Right? That's going to shift this reaction to the left, right? It's going to want to form more A, right? Because the partial pressures of B and A both will change because of that decrease in volume, which affects their chemical potentials, right? And you get twice as much change on the product side because you have twice as many gas molecules, okay? And so you're going to react some of these products to form more reactants in order to decrease those pressures, and to decrease the chemical potential of the products and increase the chemical potential of the reactants so that they eventually equal again, right, to be back at equilibrium. Yeah. And so, yeah, right? And so the same type of thing is related with changing with dilution, right? That you'd have the same type of an effect kind of going on, right? So the chemical potentials are related with the concentrations of your reactants and products. So it just depends on how many aqueous species you have in the reactants versus products, right? That's how that affects it. Okay. What about adding a catalyst? No, right? Adding a catalyst does not. Okay. And so we just talked about changing pressure by changing the volume. Okay. Right. We've talked already about adding or removing reactants, right? 5B here is the same thing as 1, right? That if I add or remove reactants, right, changing their concentration or changing their pressures, right, it's going to affect the equilibrium, right? Okay, but what about if I add a non-reacting gas to my system? Will that affect the equilibrium? Add stress to it? Some yeses. Yes. No. Nope. Because, right, you are affecting the total pressure in your container, but you're not affecting the partial pressures of your gases, right? And the chemical potentials of each of your gases just depend on their own partial pressure, right? But the total, right, but they don't, it's not dependent on what is the total pressure in the system, right? It just depends on what is the partial pressure of your gases, which again, right, your ideal gas law, right, PV equals nRT. Nowhere in there is there like plus the pressure of some other gas, right? It just depends, the pressure of each gas depends on its number of moles, the volume it occupies, and the temperature it's at, right? And by adding an inert non-reactive gas, say like argon, to your system, keeping the volume constant, right, does not affect the temperature, temperature, volume, or number of moles of your reactants products. and so it does not alter its pressure, and so it does not take it away from equilibrium, right? Because it's not going to alter its chemical potential, so the chemical potentials of reactants and products remain the same. Okay, so increasing the pressure by or decreasing the pressure by adding or removing, say, a non-reactive gas, as long as the volume is being kept constant, right, does not do anything. It increases the total pressure in your container, but that will not affect the equilibrium reaction because, again, the partial pressures of your reactants and products remain unchanged, right? You're just increasing the total pressure by adding more of some other gas to your system. Okay? Right, and then what about temperature? Yeah, temperature, right, will affect equilibrium, right? Catalysts don't, right? Catalysts just speed up things. Okay, open reactants, products faster. Okay, it does not affect equilibrium itself. Okay, we kind of talked about these things, right? Here, just showing, right, what happens, right? You add some of, say, H2, right? You've added H2 that's increased the chemical potential of your reactants for, I guess I don't have the reaction right, but the reaction is H2, what is it? The 3H2 plus 2, no, 3H2 plus N2 going to 2NH3. I think it's the chemical reaction here. Yeah. Like the Haber-Bosch cycle or reaction, right? Form of ammonia. Very important chemical reaction for industry. Anyways, right, so that chemical reaction, right, N2, H2 are reactants, NH3 is the product, right? I added some amount of a reactant after this had been established equilibrium, right? We knew it was at equilibrium because the concentrations are unchanging with time, okay? Right, what that's done is that's increased the chemical potential of the reactants. So I got to get rid of some of those reactants to decrease its chemical potential and increase the chemical potential of the products so that the chemical potentials of the reactants and products come back to the being equal, okay? And so I got to remove some reactants, and that means I have to remove both H2 and N2, right? The net concentration of H2 did go up because I added some H2 in the system, right? But the concentration of N2 decreased, and the concentration of NH3 did increase, right? Yeah. Right, but that's right, kind of what's happening in the chemical reaction again, and this is, you know, Le Chatelier's principle, if you will, that this occurs, right? Now we have a better understanding why things occur and such nowadays than back when Le Chatelier's principle, right? Le Chatelier came up with this idea, but you know. Right. Okay. All right, so we have a chemical reaction given above, a bunch of different reactants, products, different stoichiometric coefficients, different phases, and we got the enthalpy of this reaction is greater than 0, so it's an endothermic process. The question is, right, for each of the following stresses, predict the direction the equilibrium will shift following the stress to return to equilibrium, right? So if sum of C is removed from the system, will the equilibrium shift to the left, meaning it will form more reactants? Will there be no change, or will it shift to the right and form more products? Yeah, C here, when you remove some of the reactant C, it will shift to the right to form, or sorry, some of the product C, right? It will shift to the right to reform some of those products that you've just removed, right? So shift to the right. If I add B, shift to the right again, right? Because in this case, now I'm adding some reactants. Okay, it's increasing the chemical potential of the reactants. So I got to reduce that chemical potential and increase the chemical potential of the products so that they equal again, right? So it's just going to shift to the right. It's going to use up some reactants. Oh, that B thing was supposed to, okay. Well, ignore the B is added, right? Some of A is removed from the system is the question. So there will be no change because A is a liquid, right? Right. Again, liquids and solids, right? Their chemical potentials are related with their densities, right? And those are going to be unchanged with the total amount that you have, right? As long as there's some amount of A there, right? So in these problems, right, you're not you're never assuming that you remove all of A, right? If I removed all of A, then sure, it would go to the left to form some A, right? But as long as some A is there, then you're fine. Okay? And it will not change the equilibrium. Okay? All right. Yeah. Right, and so, right, again, the Lechatelier principle talked about temperature changes, right? And we'll talk about that in a second, okay? We talked about volume changes, right, and how it favors the direction that has fewer moles of gas when you increase the pressure, or greater number of moles of gas when you decrease the pressure, right? And if the number of moles in the reactants products are the same, then nothing happens, okay? Right? Because then the chemical potential of your reactants and products change equally, so it doesn't break it from equilibrium. Okay. Again, we talked about these three different things, right? About how they affect pressure or affect the equilibrium. Okay. Let's see here. Right, and I guess we'll do that slide. But so questions about this, again, I'm kind of breezing over some of this stuff because hopefully we've seen this stuff in general chemistry and it should be somewhat familiar. You know, hopefully I'm sparking some old, sparking up some old brain cells or something like that that maybe haven't been used in a while. Right. So any questions are kind of about this stuff, about what things affect chemical equilibrium, what don't? Right, and if we're uncertain, right, as to whether or not things are deviate from equilibrium and how they will readjust, right, you can always calculate the reaction quotient Q, right, which is a reminder, right, the reaction quotient Q is just the same expression as equilibrium constant K, just non-equilibrium values, right? And then based off of whether or not Q equals K or is greater than K or less than K, tells you how your system will readjust to reestablish equilibrium, okay? Right. And so, right, let's talk. And then here, for temperature, right, so I have another chemical reaction. This time it's exothermic, right, delta H is less than 0. I decrease the temperature for this. Will it shift to the left, to the right, or no change? So we got to the right, right? So how I present this in general chemistry, we're going to see more quantitatively where this comes from in a minute. But qualitatively, right, whether or not things shift to the left or right, if your reaction is exothermic, that means heat, right, is a product, right? It's giving off heat. So you can think of it as a product in your chemical reaction. And decreasing the temperature is effectively decreasing the available heat, right, if you will. And so that's removing some product. And so a decrease in temperature for an exothermic reaction causes the equilibrium to shift to the right, right, to form more products. And so, yeah. So A here to the right is what will happen when you decrease the temperature from 330 Kelvin to 298 Kelvin for an exothermic reaction, right? An endothermic reaction has the exact opposite effect, right? All right, so let's get at how we actually can calculate how this equilibrium is changed based off the temperature, okay? We'll do that by showing this Hoff equation, okay? To get there, we start with the equation we had from Friday, which is the relationship between the equilibrium constant K and the free energy of your reaction at standard states. Okay, I'm going to use the fact that the free energy under constant temperature pressure conditions, right, is just related with delta H minus T delta S. Simplify that, you get this equation here. Okay. Assuming these things are independent with temperature, right, you're to take the temperature derivative of this equation. You'd get that d ln of k dt is equal to delta H at standard conditions divided by RT squared. Okay. right? So just taking the temperature derivative of this equation here, assuming delta H and delta S are constant, just get that. Okay, this is that same equation as the previous slide. If you rewrite this equation in terms of 1 divided by temperature, you can get that the derivative of the natural log of K is just divided, the derivative of the natural log of K with respect to 1 over temperature is equal to minus delta H divided by R. Okay, so this again uses this change of variables. Okay, and the reason I present form 2 here is just for the fact that to get the enthalpy of a reaction, right, often what's done is you can measure the equilibrium constant at varying temperatures, plot the natural log of that equilibrium constant versus 1 divided by the temperature, and you will get a straight line, right, assuming enthalpy is constant, and that straight line is just going to be the enthalpy of the reaction divided by R. This is a very common way to measure the enthalpy of a chemical reaction by measuring the equilibrium values of your reactants products at different temperatures, right? Okay. This is more so done, I'd say, probably for like electrochemical reactions and such, right? For say combustion type reaction, things like that, you just use like a calorimeter to get these enthalpies and such, right? But for an electrochemical reaction, right, you can get the potentials and relate that to concentrations and other things like that. Or more, you can just measure the potential, relate that to your equilibrium constant at a given temperature. It's related to the electrochemical potential, which we'll talk about. Okay, and then you can use that to get the enthalpy change for that electrochemical reaction. Yeah. Right. So, right. But if we go back to equation 1 here, form 1, right, this d ln of k dt equals delta H by RT, okay? Right, you kind of looking at this, right? If delta H is less than 0, that means that this d ln of k dt has to be less than 0, right? So that if t increases, k has to decrease, right? Because if one of these increases, the other one's got to decrease because this is negative, right? It's got to be less than 0, okay? Right, and so this kind of gives you this what we just talked about in terms of if you have an exothermic reaction, right? The fact that as temperature increases, the equilibrium will shift to the left, or if temperature decreases, the equilibrium will shift to the right. Okay, right. But if we want to take that equation and integrate it out, okay, from some initial to final states, right? You just get this equation here. Oh, thought I had it highlighted, but no. Right, the natural log of k final over k initial equals minus delta H over R times 1 over T final minus 1 over T initial, right? This equation should look somewhat familiar. This is a similar looking equation to how the right, the vapor pressures of a liquid changes with changing temperature, okay? Right, the difference here is instead of enthalpy of a reaction, you have enthalpy of vaporization, right? But really, this equation and that change in vapor pressure with change in temperature equation are essentially identical, right? Because if you think about it, right, the vapor pressure is related with the equilibrium between the liquid and the gas. Well, the equilibrium constant for that equilibrium reaction of liquid going to gas is just the pressure of the gas, right? So the equilibrium constants just become pressures of your gas. And then delta H is just the enthalpy of vaporization, right? Because that is your reaction, is the vaporization reaction, right? So that equation that we derived before, right, that has this exact same type of form for vapor pressure changes with temperature, okay? Right, these are directly related, right? They should be related because they're obtained from the same thing, which is how Gibbs free energy depends on these things and how chemical potential changes with temperature and things of that nature, okay? So they should end up being related. But this is a very similar functional form than equations we've seen before, right? The bottom line here is just me rewriting this to solve for K if you wanted to, but you don't need to, right? But so this quantitatively tells us how the equilibrium constant changes with temperature, right? And that's why your equilibrium, right, shifts with a change in temperature. It's not because it affects the pressures and whatnot of your gases or potentially or the concentrations, right? But the fact that it changes the equilibrium constant itself, right? the equilibrium constant is dependent upon temperature. This relationship shows us how it depends on temperature, right? And so as your equilibrium constant increases or decreases, right, that affects whether or not you have more reactants or more products, right? And so, yeah. Okay. So questions about this Van Hoff equation? Okay. Here, natural log, K final, K initial, blah, blah, blah. Okay. Right. I would never use this equation to figure out, whether or not, answering a multiple choice question, kind of like this one, right, as to what direction this thing equilibrium shifts to the left or right, because it's way more complicated than needed, right? But this is a very useful equation if we're ever curious, right? What is the equilibrium constant for some reaction at a different temperature? Okay. Right. Or again, if I'm trying to get the enthalpy of a reaction given different equilibrium constants at different temperatures. All right. So questions about kind of Charlotte's principle, right? What things affect chemical equilibrium? How do we reestablish them? This Van Hoff equation. So let's do some wonderful equilibrium problems that I'm sure everyone loved when they were in general chemistry. Love again. Have you, in analytical chemistry or some other type of chemistry, have you dealt with this at all since Gen Chem? See some no's, some yeses. So I don't know. I guess it depends on your faculty or I don't know what classes you've taken since then. I don't know. All right. But yeah. So let's say I have a sealed container, right? So constant volume, right? System, right? I fill it with 0.3 moles of H2, 0.4 moles of I2, 0.2 moles of HI, 170 Kelvin, right? And the total pressure in this container is 1 bar, okay? So the volume is whatever it needs to be such that the total number of moles given there has a total pressure of 1 bar. The question is calculate the amounts of each gas at equilibrium given that the equilibrium constant K is equal to 870 for the reaction H2 plus I2 going to 2HI. All right. Right. So if I want to know what are the equilibrium concentrations of, or pressures or whatever of these different gases, H2, I2, HI, given the equilibrium constant is equal to 870, right? I need to use that equilibrium expression, right? Which is going to be concentration, or I guess not concentration, right? Pressure of H. Let me do this. The, equilibrium constant, right, is equal to the pressure of HI squared over the pressure H2 times the pressure of I2, right? Is what this is related to, right? But these are all equilibrium values, right? Right, so the equilibrium pressures and such, right, which I don't know what they are off the top of my head, right? And that's what we're trying to find, okay? And so, right, so the first thing I need to think about, right, is, well, what are my starting pressures, right? Well, right, I'm not given the pressures of each of these gases, I'm given the moles and the total pressure, and I can calculate their partial pressure, right, using the mole fraction, right? Pressure of A is just mole fraction of A times P total, right? And so when you do that, my total number of moles here is 0.9. So the pressure of H2 initially, right, put like a little knot here, right? The initial pressure of H2 is just equal to 1/3, right? Bars. Okay. Initial pressure of I2 equal to 4/9. Okay. Right, and the initial pressure of HI is equal to 2/9. Okay. These are all bar, right? Okay. Right, but right, these are the initial pressures, not the equilibrium pressures. Okay, and we know this thing's going to reach equilibrium. So you can figure out what direction the reaction is going to go by, say, calculating Q, which again is the equilibrium constant expression. Just plug in these values here and compare it to the equilibrium constant. Just kind of looking at this, right? I can already tell 2/9 divided by 1/3 times, or 2/9 squared divided by 1/3 divided by 4/9 doesn't look like it's going to be as large as 870. So I'm pretty sure I need to form more products and use up some of my reactants here. But again, you could calculate it, and on the slides, I'll have that calculation, okay? But the idea here is that I'm going to lose, right, in my reaction, H2 plus I2 going to 2HI, right? I'm going to lose some of H2, some of I2, and I'm going to gain some of HI, right? You can do this if you want to using an ice chart to kind of keep track of things if you feel like it, right? 1/3 initially, 4/9 initially, 2/9, right? So minus x plus 2x, right? So 1/3 minus x, right? 4/9 minus x, and 2/9 plus 2x, right? And then we can plug in these equilibrium values back into our expression here, k, which equals 870, then equals 2/9 plus 2x squared over 1, which would be 1/3, 1/3 minus x times 4/9 minus x, right? And so this gives me an equation. I can solve for x, okay? Right. So we go back. We can go back to slides here, so I don't have to plug in numbers right. But for example, again, if you calculate the reaction quotient Q and put the pressure of HI, which is 0.22, divided by the pressure of H2 and the pressure of I2, which is 0.23 and 0.44, okay, you will get a Q of 0.33, which is less than K, right? So I got to lose some reactants and form more products, right? So again, I have this equation here that I have to solve for I, okay? When you solve for x, solve for x, you'll get answer 0.322 or 0.45, right? This has two potential answers because it's going to have the quadratic equation, okay? Well, 0.45, right, my reactants, I start off with 0.33 and 0.44 of both of my reactants. There's no way I can lose 0.45 of either of these guys because that's more than what exists. So 0.45 is not a possible answer, so the answer has to be 0.322. Okay. And so, right, the pressures then of I2 and H2 are just 0.33 minus 0.322 and 0.44 minus 0.322. And the pressure of HI is 0.22 plus 2 times 0.322, right, which gives us 0.864. So those are the equilibrium pressures, okay? Here, I guess I calculated the final moles. Is that what was asked in the question? Let me see here. Amounts of each gas, yeah. So, I mean, you could have left it as pressure. It didn't really say. You could calculate the moles. Here, I use the fact, right, that right, the total number of moles is unchanging because they go from 2 molecules to 2 molecules, right? So total moles of stuff is unchanged. I know N total is 0.9. And so using that, right, basically take these guys and multiply it by 0.9 to get the final number of moles. Oh, that shouldn't be bar. I don't know why that's bar. Yeah. Right. Right, because again, and also because, right, the total number of moles is unchanging and the volume we're assuming is unchanging, right? It's in a fixed volume container, right? So the volume's unchanging, total number of moles is unchanging, right? Total pressure is still 1 bar, right? This container, as the reaction's going, the total pressure still remains 1 bar. And so I know that these pressures, right, are just related to the mole fractions because I divide each of these partial pressures by their mole fractions, or by the total pressure of 1 bar to get the mole fractions, right? And so, right, and then I took those mole fractions multiplied by the total number of moles of 0.9 to get the final number of moles of each of those species. Okay?
What was the reason behind solving for K equaling 0.33?
Q. Finding Q equal 0.33 was just, if I didn't really have an idea of which direction the reaction was going, this could tell me. Now, technically, even if you guessed the wrong direction, you'd still be able to get the same answer, right? Because basically your X values would be like negative 0.322 and negative 0.45 or something like that, right? And so it being a negative would just tell you, oh, I guessed the wrong direction, right? But so yeah, so you don't have to do that, but I kind of present it, show it here, right, as a refresher of something that potentially you did in Gen Chem, right? But yeah, so the point of calculating Q is just to see what direction the reaction goes, and by comparing the sides of Q to K. Other questions? All right. Right, so another example here, question is, what is the standard enthalpy of a reaction? For a reaction that has its equilibrium constant doubled when the temperature is increased by 25 Kelvin at 310 Kelvin, right? So I start at 310 Kelvin and I increase the temperature to 335 Kelvin and the equilibrium constant doubled. What is delta H for that reaction? All right, so this question, right, is basically just using that Van Hoff equation, right? Right, natural log of K final over K initial equals minus delta H of the reaction, right, over R times 1 over T final minus 1 over T initial. I think there's that minus sign there. We'll see. Yeah. All right, right? So in this case, right, the equilibrium constant doubles, so this is just the natural log of 2, right? And then minus delta H that we're looking for over 8.314, okay? And then the temperatures, the final temperature is 335 Kelvin. The initial temperature is 310 Kelvin, right? Because you're told the temperature increases by 25 Kelvin, right? Or 25 Celsius, which is still 25 Kelvin, right? From an initial temperature of 310 Kelvin, okay? So basically, we just got to plug in these numbers and solve for H, okay? So we'll go back the slides here. That's done, right? So here I used the kind of rearranged form. Okay, fine. I don't know why I would do that. That doesn't make sense. Yeah, because I don't know why I started with that equation here. Yeah, because that's basically what I did right here is I have, this is the temperature, 1 over the temperature difference, right? 1 over T final minus 1 over T initial is divided by R is this right here. And then I have the natural log of 2. So yeah, I don't know what the heck I was doing. Right. So note here that this temperature difference is going to be a negative number, right? Because T final is greater than T initial. And so 1 over T final minus 1 over T initial has to be negative, right? And so that's going to cancel out this negative to make this overall thing positive, right? So that's how I get a positive 2.895 times 10 to the minus 5, right? And so solving for delta H gives us this in joules per mole. And then just if I want converting it to kilojoules, right, I get 23.94 kilojoules per mole is the enthalpy change for this reaction. And it is an endothermic thing, right? K increasing means it's favoring products, right? Right, the larger value of K, the more you're favoring products, right? And K increased with an increase in temperature, which tells me that it has to be an endothermic reaction, right? Because an endothermic reaction, as you increase temperature, it shifts to the right, right? Forms more products, and so that will produce a larger value of K, right? So my sign of delta H here is correct. It should be endothermic. Questions about this problem? Questions about equilibrium problems? Maybe about some things. Again, we brushed over a number of things in class today that are hopefully kind of refresher stuff. But if it's not so fresh in your memory, right, I'm happy to answer questions about anything dealing with equilibrium, ice tables, and solving equilibrium problems or anything like that. All right, if there are no questions, then that's it for today. And I will see you guys on Wednesday, which again, you have a homework due on Wednesday.